Hello everyone, today I will present a paper from the Google Brain teams with the title TensorFlow, a system for large-scale machine learning. It appeared on OSDI 2016. TensorFlow is a machine learning system proposed by the Google. It operates on large scale and in heterogeneous environments. It uses data flow graphs to represent computations, share state, and operations. It maps the nodes of a data flow graph across many machines in a cluster. This architecture gives developers more flexibilities. It enables developers to experiment with normal optimizations and training algorithms. TensorFlow supports a variety of applications, with a focus on training and inference on deep neural network. About their motivations, actually TensorFlow is the successor to Disbelief, which is the distributed system for training neural network for Google has used since 2011. Disbelief was scalable and good for production deployment, but not for research purposes. And secondly, researchers often want to experiment with new optimization methods, but doing that in disbelief involves modifying the parameter server implementations. So they want to refine the training algorithm. And because disbelief workers follow a fixed execution pattern, and this pattern fails for more advanced models. So they want to define a standard ways of expressing machine learning ideas and computations. Fourth, they want to short circuit the magnitudes or Hadoop inefficiencies caused by the synchronizations communications. Here is the major contribution of their papers. They TensorFlows use a single data graph to represent all computations and the state in a machine learning algorithm, including the individual's mathematical optimizations, the parameters, and the update rules. The data flow graph expresses the communications between sub-computations. So, it is easy to execute independent computations in parallel and to partition computations across multiple devices. TensorFlow differs from the batch data flow systems in two aspects. The first is the model supports multiple concurrent execution on overlapping subgraphs of the overall graph. The second is that individual vertices may have multiple states, and it can be shared between different executions of the graph. Data flow with multiple states enable TensorFlows to mimic the functionalities of a parameter server, but with additional flexibilities, because it becomes possible to execute arbitrary data flow subgraphs on the machines that hold the shared model parameters. They achieve that with the tensors. In a TensorFlow graph, each vertex represents a unit of local computation, and each edge represents the output flows, or the input to a vertex. They refer to the computations at vertex as operations, and the value that follows and the value that flows along edge as tensors. In TensorFlow, they model all data as tensors, with the elements having a small number of primitive types, and tensors naturally represent the inputs tools and the results of a common mathematical operations in many machine learning algorithms. The second technique is the state variables. An operation can contain multiple states, and it can be read or wrote each time when it executes. A variable operation owns a multiple buffers that may be used to store the shared parameter of a model when it is changed. A variable has no inputs and produces a reference handle, and it acts as a type capacity for reading and writing the buffer. The first technique is uh, the distributed executions. Data flow simplifies distributed executions because it makes communications between subcomputations. It enables the same TensorFlow programs to be deployed to a cluster of GPU for training, a cluster of TPU for serving, and a cell phone for mobile inference. Each operation resides on a particular device, such as a GPU or CPUs in a particular task. A device is responsible for executing a kernel for each operation assigned to it. TensorFlow allows multiple kernels to be registered for a single operation with specialized implementations for a particular device or data type. Here is the evaluations of their proposed systems. They compare their performance with the MaxNet, another famous deep learning architectures. From the figure 1, we can see that TensorFlow achieves slightly better throughput than MaxNet for asynchronous trainings. And from the second figures, asynchronous and synchronous training throughputs increase with up to 20 workers. And in the third figures, to reduce the overall stack times and improve the performance, they add the backup workers to a 50 workers training jobs. That's all the presentation, thanks.